Good afternoon, and welcome to the second talk of Cambridge Life Festival. In this talk, we're going to talk about how, if a nuclear reactor produces an energy in a safe and reliable manner. A bit of a background. There are considerable changes in how our climate behaves, more which are related to carbon dioxide levels, as you can see on the left graph over there. And then on the right-hand graph, on the right-hand image, there is a video from YouTube showing the average temperature from 1880 to 2020. And as you can see, the temperature of the Earth is like slowly over the years increasing. Like the climate has become more and warmer because we're emitting more and more carbon dioxide levels and other gases into the atmosphere. Now, climate change can have numerous effects on the which can be both to nature and to humanity. This can range from bleaching of corals in the oceans, wildfires that burn like massive amounts of like forests, melting of ice caps with polar bears starving because they can't survive in anything that's not like only water. And then to humankind, it can be like results like crop failure due to drought and flooding in coastal towns and cities, like Venice. So to combat this, we have to think of solutions to minimize carbon emissions. Like one obvious solution can be using renewable sources. Now, the term renewable means that energy can be generated perpetually. You don't run out of fuel. It's carbon-free, which means that you don't produce anything, at least in the energy generation stage. It has multiple forms, which can lead to sustainability if we combine them in a proper manner. So there are 5 major sources of that, which are hydro, solar power, wind turbines to capture from wind, hydrothermal power through geysers, and tidal energy harvested by numerous techniques, such as these arrays shown in this picture. Now, however, renewable energy sources have some disadvantages. One of them being the lack of versatility. The biggest advantage is versatility because the output can be easily increased or decreased to comply with demands changes. However, they have a very bad disadvantage of intermittency, and that's because it's not always sunny, it's not always windy. We don't have always high tides, and various other things like that. And to make this worse, batteries, which are used to store the energy collected from the sources, can store up to a point. We haven't developed the energy to meet the demand yet. And the other potential disadvantage is its low density, which it's just that the power ratings of these techniques is like low and cannot be used to cover our needs. Like one example is Germany, who had to stop the nuclear power plants, and as a result had to start back their coal and oil and gas factories because they couldn't meet the demand. So how are we going to solve this? Nuclear is carbon neutral, at least in the generation, which is the same with for renewables, because we have emissions from mining, manufacturing, and transport of the materials we need. It's energy dense, as you can see in this image over there, more energy dense than wind and solar and hydropower, to the same extent as coal and natural gas, but without the emissions the former to produce. And on top of that, it's also heavily regulated, so it leaves a very tiny room for deviation, which means a very small probability of things going bad. And as you can see, if you exclude the major sources, the major land, the energy sources that require a lot of land, and then if you exclude the ones that produce carbon, then what you are left with is essentially nuclear power. So a bit of physics. Conventional reactions, when we burn like gas or even like petrol and diesel in cars, are chemical reactions like the one here, with this image representing the burning of methane. So these are chemical reactions. What we use in nuclear is nuclear reactions, such as fission, where heavy nuclei like split into smaller ones, and fusion, where light nuclei fuse to form heavier ones. Because of this chemical reactions and the interactions of electrons in atoms, which means that you can change compounds, but the nuclear will still be the same. An element is not going to change to another element. That's not the case in nuclear, where you will have a uranium producing krypton and barium, which is like different elements altogether. And because protons and neutrons in a nucleus are much more bound than electrons in nuclear structure and atomic structure, respectively, the output of energy can be much higher. In fact, the scale can be a million times higher, and the energy you can produce from a kilogram of uranium-235, which will be 33 kilograms of reactor-grade uranium, is the same energy as you would gain from burning 3 million kilograms of coal. In here, you can see fusion and fission in a graphical manner. As you can see, the left-hand graph is showing fission, like when a neutron collides in the uranium nucleus, it splits into smaller nuclei along with a few neutrons, which will cause subsequent fissions, creating a chain reaction, which will give us energy. On the right-hand side is the hydrogen 1, hydrogen 2 fusion reaction, where these two nuclei are like joined together, producing helium-3 and energy at the same time. So this is a schematic of how a nuclear reactor works into action, as you can see. So in short, uranium undergoes fission, produces heat. This heat is transferred through this primary circuit to this primary circuit, which remains liquid at all times in this specific design because of this pressurized over here. This water will boil off a second circuit of water, which will turn into steam, which will rotate turbines, which turbines are adjusted to a power generator, which then feeds the grid. The steam after that will be condensed back into liquid, usually through a local well or such as like a river or the nearby sea, become back to water, back into the reactor to extract heat from the primary circuit and begin the cycle anew. The control rods is what controls the reaction. By putting them in, we reduce the output. By taking them out, we increase the output. So there are multiple fission reactors. The one on the previous schematic is a PWR, it means pressurized water reactor. Pressurized means because of the water is pressurized, the water in the primary circuit, the first circuit, is pressurized to not boil. But however, there are other types of fission reactors. Fission reactors will all use uranium and will split them into smaller nuclei, lighter elements, and then produce energy as a result of this process. The neutrons, however, are much more energetic than we need to, so we need to slow them down. This is the property of a moderator. In a PWR, in all water reactors, the water, in addition to being the coolant, The material that cools down the reactor is also the moderator, which slows down the neutrons and causes them to maintain the fission output. How this type of a reactor is common in the world, but not so common yet in the UK. The UK uses a different design, which is called an advanced gas-cooled reactor. An example of this reactor is Hinkley Point B on Somerset, which is like being shown in the left-hand side image in this slide. And on the right-hand side is a simplified schematic of that reactor. In this reactor, uranium undergoes fission. We use graphite as the moderation. The graphite is the material that will slow down neutrons to ensure the propagation of fission reactions over the uranium. The heat is extracted through carbon dioxide, which then follows a similar circle. It will boil an input of water of a different circuit, which will then become steam, rotate turbines, and produce electricity as a result. The second reaction which we can use in nuclear power is fusion. Fusion is how the sun produces energy. Essentially, it's taking small atoms and joining them together to form bigger ones. The sun and most of the stars, for example, use primarily hydrogen and are joining them to make helium and produce energy as a byproduct, essentially. You require, however, massive temperatures for that. You need temperatures in the order of tens or hundreds of millions of degrees centigrade. So how are we going to achieve this? With devices like this. This is called the tokamak, and you will listen to that in detail in the fusion talk. In here, we compress hydrogen in massive pressures and temperatures. This conditions causes hydrogen atoms to fuse together and create helium atoms, and then we capture the heat, and in a similar manner, we extract the heat by boiling some water and putting it through a steam, and we produce it as electricity through turbine rotating. So we saw how these reactions are, but how are we gonna make sure that we have safety? Up till now, we know about safety in fission reactors because these are the ones we currently use. So one thing we can use is the control rods we spoke about earlier. You can see a schematic of them in the right-hand side. Essentially, a control rod is the gas and the brake pedals of a reactor. They're made from materials that can absorb neutrons, which essentially can stop nuclear reactions from propagating. This can help modify the output. We put them in to reduce the output of the reactor. We'll take them out to increase the output of the reactor. And if we want to fully stop it, we put them fully inside. The second safety feature is the redundancy concept. More often than not, you will find that in a nuclear reactor, we will use more equipment that we need to. For example, a nuclear reactor may require 2 cooling pumps. We will install 4 on that system, as you can see in the image over there. This ensures a backup in case, for example, that 2 of them go wrong and stop working. We have the other 2, so we can still maintain the reactor being operated. Other safety measures we can employ are to separate the radioactive and non-radioactive parts. So this is the reason why we use 2 cooling circuits. One of them will have water that will inevitably be radioactive because it comes into contact with uranium. However, the second circuit is always a different one, so the water in the secondary circuit is non-active. Furthermore, everything that's radiation related in a nuclear power plant is going on the same vicinity in which is termed the nuclear island. And also one example is like this figure over here, where basically we have things like the fuel handling area, the reactor core on one side of the building, and always being domed by a massive concrete structure that prevents release of radioactive material, which concrete structure can even withstand an airplane crash. And then everything else, such as like the turbines, are on the non-active side of the plant. Another thing we utilize is the concept of negative feedback, which basically means that if we have an increasing of power we didn't plan, then the phenomena that will result will automatically decrease the power and imbalance the whole plant. As an example, we use water as a moderator. If the temperature of the water is increased because the power was increased, then the water will dilate. We will have less moderation as a result, so a less power output, and that will rebalance things. And if everything else fails, we have the final, an ultimate ability we can use. It's like the SCRAM. SCRAM is an acronym. It means Safety Control Rod Axeman, and basically we'll put the control rods fully inside the reactor to stop it immediately. This term comes from the first nuclear reactor experiment in which there was a person with an axe ready to chop the ropes that were holding the control rods. Whereas if, at which case the control rods will fall inside the pile, stopping the chain reaction from continuing. And this is a button that the button on the interface on the control room of a nuclear reactor that still have kept the same acronym. You may know it as AZ5 from the TV series Chernobyl, but in the UK it's most commonly called SCRAM. So to conclude, is a nuclear reactor safe? Environmentally, it is, because it requires a smaller amount of land if you compare it with renewables. It produces a much less CO2 emissions if compared with fossil fuels. And the waste problem is sorted by putting the spent fuel in repositories. Financially, it's also safe because it will increase energy supply, and that will reduce electricity costs, and it will create new jobs, both during the construction and the operation phases of a reactor, and also during the decommissioning. You have risks, however, that bring from nuclear, as an example being that if you have a release of material in the environment, the consequences might be severe, but we can mitigate that if we mix nuclear with renewables, because that combination probably is the best solution we may have to reduce CO2 emissions and tackle climate change. And that's the end of my talk. Thank you very much. I'm happy to listen to any questions you may have.